Okay, so we've done a few videos so far on the calculus of parametrics. Been focusing mainly on the derivative and the second derivative. Uh, Finding out how to take them, finding out how to evaluate them, using the evaluation of the first derivative to find equations of tangent lines. We're going to continue to do a little bit more of that. In your book, there's a short example of how to find the area under the curve using parametrics. Um, that's rarely asked because it's such a specific, it has to be a curve that you can actually find an area under, meaning it doesn't double back on itself and all sorts of fun stuff like that. So we're not going to concentrate on that. There is that one example in your book, and if you're interested in looking at it, I'll point you in that direction. We're going to continue on talking about sort of the application of the derivative, and then we're going to move on to arc length and surface area, which are used far more often than finding the area under the curve. In fact, except for the one in the book, I don't think I've ever actually encountered one on an AP exam or anything like that. Usually it's just not what they focus on. So let's go ahead and let's let's keep talking about tangent lines. Okay, let's say that I'm given x is equal to t squared minus t plus 2, and y is equal to t cubed minus 3t. And let's say that after having been given that, I'm asked if there are any horizontal tangent lines and if there are any vertical tangent lines. Okay? Well, I know that that has something to do with the derivative, so let's go ahead and just find the derivative. Let's do dx dt, which, by the way, can be shorthanded as x prime of t. Prime, of course, being the derivative. So that's 2t minus 1. dy dt, in like fashion, can be y prime of t, and that's 3t squared minus 3. Now, I know that when I actually take the derivative dy dx, these kind of do this number. Okay, got to be really careful with that you put the right one in the numerator. And so that's 3t squared minus 3 over 2t minus 1. Now, when do we have a horizontal tangent? Well, we have a horizontal tangent line when the derivative is equal to 0. Well, in a rational expression like that, it's 0 when the numerator is 0. So let's go ahead and rewrite that derivative, and let's go ahead and put it into factored form. T minus 1 and 2t minus 1. So I recognize the fact that I'm going to have horizontal tangent lines at horizontal tangents, okay, at t is equal to negative 1 and 1, okay. I'm going to have vertical tangents, obviously, when the derivative is undefined, which means at t is equal to 1/2. Now, does that make sense? Well, let's go ahead and let's look at let's look at those that pair of parametric equations on the graph. Let's go ahead and clear those out of there. And it was t squared minus t plus 2 and t cubed minus 3t. Now let's go ahead and graph. All right. Now, does it look like there are two places where there are horizontal tangent lines and one place where there's a vertical tangent line? Actually, yeah, there is. And what you really have to do is you just have to find the ordered pairs that are associated with those t values. Now, that's easy enough. At t is equal to 1, let's go ahead and do that. So you have x, or let's do negative 1 first. That becomes negative 1 squared minus a negative 1 plus 2. Or, well, that's 1 plus 2, so that's 4. And y of negative 1 is going to be negative 1 cubed minus 3 times negative 1, or 2. So that is going to give you the ordered pair for 2. And I'm going to go ahead and change the window on this in order to be able to see it a little bit better. Does one of those horizontal tangent lines looks like it occurs at 4, 2? 4, 2. It actually does look like that. Okay, so it stands to reason that we actually did it right. Let's go ahead and look at x of 1 is equal to 1 squared minus 1 plus 2. And that's going to be 2. And we know y1 is going to be 1 cubed minus 3 times 1, or negative 2. So that's going to be the ordered pair 2, negative 2. At 2, negative 2, does it look like I have a horizontal tangent line? And the answer is yes. Okay, well, let's do 1/2. And that's going to be a little bit more difficult, and we're going to come out probably with a fractional answer. And so we're going to have 1/2 squared, which is 1/4, minus 1/2 plus 2. Okay, so that's going to be 1 3/4, or 7/4. And we have y to the 1/2. When that's cubed, it becomes 1/8 minus 3/2. And 1/8 minus 3/2 is 1/8 minus 12/8, or negative 11/8. Now it's obviously a fractional ordered pair, 7/4, negative 11/8. But that kind of makes sense out of that, where that vertical tangent line is right there. Okay, well, let's go ahead and move on to something else. Let's actually talk about concavity for a moment. Okay, let's say, and I'm always wanting to give you all the trig versions, but if I do too many trig versions, the polynomial ones will start to look a little bit alien. So why don't we do a polynomial one, and then we'll turn around and we'll do a trig one here before long. Now, if I give you this pair of parametrics and ask you, give me the t intervals on which the curve is concave up and concave down. Well, obviously I need to find the second derivative. So let's go ahead and find the first derivative. And I'm going to go ahead and flip the order. Remember, that's also called y prime of t. And I'm going to put it in descending order. So that's 3t squared plus 2t. dx dt is also what we refer to oftentimes as x prime, and that's 2t. Okay? So those two together, if you want dy dx, is going to be 3t plus 2 over 2, once I factor out the t's and actually simplify, okay? Which is also 3/2 t plus 1. And that's going to make it a little bit easier when I take my second derivative. Now remember, the second derivative is the derivative of this with respect to t over this again, okay? So d2 dx becomes d dx of dy dx, which then becomes d dt of dy dx over dx dt. Okay? Just a little reminder of how we get that, right? We basically transform this d dx into d dt over dx dt, and that's how we arrive here. And it has to do with the complications of taking the derivative with respect to x of something that is in terms of t. So up here, this just becomes 3/2, and then we put it over 2t, and we wind up with 3 over 4t. Well, if that's the second derivative and we've taken it correctly, and I think we have, obviously this is positive when t is positive, and it's negative when t is negative, and it obviously has an inflection point at t is equal to 0. So our answer is going to be concave up, where it's positive, so where t is greater than 0, or if you want to put it in interval notation, it's 0 to infinity. And it's concave down t is less than 0, or again, if you want to put an interval notation, negative infinity to 0. Be careful not to include 0, because 0, of course, is the inflection point. Let's go ahead and do a trig one real quick before we round this video out. Once we're done with this video, we'll do a little bit of arc length and surface area. Whether that takes 1 or 2 videos, I'm really unsure. It's actually really straightforward and is rather analogous to the way that we were doing it with functions earlier. Okay, so there it is, and let's say I want to figure out, obviously, if this is periodic, and it is, it's actually it's an ellipse, right? We've seen that before, so it's just going to go around and around and around and around and around again. So let's go ahead and limit ourselves just from 0 to 2 pi, okay? Now, let's go ahead and, like I said, usually it's customary to list the x first when you're dealing with a pair of parametrics, but I like to take dy dt first, largely because I'm usually going to put it physically above dx dt on the paper, and then I don't have to remember to swap them out when I'm actually putting them in the ratio dy dx. Good habit to get into if you can think about it. If not, then just hope that you don't mess that up. So you get 2 cosine t as y prime and negative 4 sine t as x prime. This winds up being negative 1/2 cotangent t, right? Because, sorry, I forgot to put the dy dx. Because obviously the 2 over negative 4 simplifies into negative 1/2, and cosine over sine is the ratio cotangent. I want to put it like that instead of in a ratio, because then I'm going to take the derivative of this again, and I want to be able to do it simply, so I don't want to have to deal with the quotient rule or anything silly like that. Now, the second derivative, of course, is going to be the derivative of this. Now, the derivative of tangent is secant squared, so the derivative of cotangent is negative cosecant squared, that negative canceling out with that negative, and giving you 1/2 cosecant squared t. Okay, and then of course you want to put it over this, negative 4 sine t. So that gives me negative 1/8 cosecant cubed t. Well, here's the thing. You simply need to ask yourself where is cosecant positive and where's cosecant negative? Well, because it's cubed, right? It's not squared. If it were squared, it'd always be non-negative, okay? Or actually always positive, because it would be undefined or positive. But here it's cubed, so you actually have to entertain the negatives of it. But cosecant, being the reciprocal of sine, is going to be positive where sine is positive. But since it's a negative 1/8 cosecant t, it's going to be positive where sine is negative. So on 0 to 2 pi, okay, sine t is positive from 0 to pi. So your second derivative is going to be negative on 0 to pi. And your second derivative is going to be positive where sine is negative, and that's going to be from pi to 2 pi. And of course you can put them in interval notation if you want. But that kind of makes sense if we actually look at the graph and actually watch it get drawn. Let me go ahead and type this in. X is 4 cosine t, and y is 2 sine t. And we're going to go to the window and make sure that it's 0 to 2 pi. Okay. Let's go ahead and go negative 5 to 5. Delete. And graph. See, it starts here at 0, concave down for the first half, and then concave up for the second half. Concave down for the first half, concave up for the second half. So it makes sense, especially in light of watching our calculator draw it. Okay. Okay, like I said, that kind of does it with derivatives for parametrics. We'll deal with integrals starting in the next video, and however many videos it takes us to actually get through a sufficient number of examples. But like I said, we're going to be concentrating on arc length and surface area. And if you don't remember arc length and surface area with respect to just functions that we've done in the past, go ahead and look back at 8.1 and 8.2 in your book and the notes associated with those. Okay. As always, if you have any questions, please do email me. Bye.